In today's video, we will be going over how to solve linear first-order differential equations. For our first set of problems, we have been asked to find a function that is the solution to the given differential equation. In order to solve each of these, we must first get them into the particular form of dy over dx plus some function p of x multiplied by y is equal to some function q of x. And so for this first problem, it is already in that form, and so we can say that p of x is equal to 4 multiplied by x. We can use this to identify our integrating factor, rho of x, as being equal to e to the integral of our function p of x, so 4x dx. From there we find that rho of x is going to be equal to e to the 2x squared. And so we take this integrating factor and multiply it by each term in the equation. And so we have y prime times e to the 2x squared power plus 4xy times e to the 2x squared power is equal to x times e to the 2x squared power. From this, we can see that the left-hand side of our equation is equal to the derivative with respect to x of y multiplied by e to the power of 2x squared. This is because you use the product rule to solve this. The derivative of y will be y prime times e to the 2x squared, and the derivative of e to the 2x squared is 4x times e to the 2x squared multiplied by the other half, y. And this will be equal to x times e to the 2x squared. At this point, we can take the integral of both sides of this equation. The integral on the left-hand side will cancel with the derivative, and so we have y times e to the 2x squared is equal to the integral of x times e to the 2x squared with respect to x, so dx. The solution to this integral will leave us with y times e to the 2x squared is equal to e to the 2x squared over 4 plus some unknown constant c. Dividing e to the 2x squared to the other side of our expression, we get our function y is equal to 1 over 4 plus some constant c multiplied by e to the negative 2x squared power. For our next function, to get it into the form dy dx plus p of x times y is equal to q of x, we must divide all of the terms by x, and so we get y prime plus 5 over x times y is equal to 4x squared. From this, we can find our function p of x is equal to 5 over x, and from this we can find our integrating factor rho of x is equal to e to the integral of 5 over x dx. Solving this integral and simplifying, we find that rho of x is going to be equal to x to the 5th power. And so we take our integrating factor and multiply it by each term in the original expression. And so we get y prime times x to the 5th plus 5x to the 4th times y will be equal to 4x to the 7th, and that is our integrating factor multiplied by this original expression. The left-hand side of our equation is the exact same thing as the derivative with respect to x of y multiplied by x to the 5th power, and that will be equal to 4x to the 7th. We once again take the integral of both sides. The integral cancels with the derivative, and so we have y times x to the 5th power is equal to the integral of 4x to the 7th dx. Solving for this integral, we wind up with y times x to the 5th power is equal to x to the 8th over 2 plus some unknown constant c. Dividing both sides by x to the 5th, we get our function y is equal to x to the 3rd over 2 plus some constant c multiplied by x to the negative 5 power. For our last problem, we are given x multiplied by y prime plus 2 times y is equal to x squared minus x plus 1. We first need to divide by x to get our function into this similar expression, and so we get y prime plus 2 over x multiplied by y is equal to x minus 1 plus 1 over x. From this, we get our function p of x as being equal to 2 over x. From that, we can get our integrating expression rho of x is equal to e to the integral of 2 over x dx. Solving this integral and simplifying, we find that this is equal to x squared. Multiplying this integrating factor to each term in our original expression, we get y prime times x squared plus 2x multiplied by y is equal to x to the third minus x squared plus x. The left-hand side of our equation is the same thing as the derivative with respect to x of y times x squared, and this will be equal to x to the third minus x squared plus x. We can then take the integral of both sides of this equation. The integral will cancel with the derivative on the left side, and so we get y times x squared is equal to the integral of x to the third minus x squared plus x dx. Solving this integral, we get y times x squared is equal to x to the fourth over 4 minus x to the third over 3 plus x squared over 2 plus some unknown constant c. Dividing the entire equation by x squared, we get our function as y is equal to 1/4 times x squared minus 1/3 times x plus 1/2 plus c multiplied by x to the negative 2 power. For our next problem, we are told that a tank initially contains 70 gallons of water. Brine containing 3 pounds of salt per gallon flows into the tank at a rate of 5 gallons per minute. The mixed solution then leaves the tank at a rate of 3 gallons per minute. They have asked us to find an expression representing the amount of salt in the tank at a time of t. We can begin this by knowing that we are going to represent the amount of salt in the tank at any given time as the variable x. And so we know that the change in x, or the change in the amount of salt in our tank with respect to time, is going to be equal to the amount of salt flowing in. And so we have 5 gallons per minute times 3 pounds of salt. And so we have 5 multiplied by 3. And we subtract from that the amount of salt flowing out of the tank. And so we have minus 3 gallons per minute multiplied by the unknown concentration of the salt in the tank, C sub 0. By noting that the volume of our tank is initially at 70, and we are gaining 5 gallons per minute and losing 3 gallons per minute, we have a change of plus 2 gallons times time t is our volume. And so our concentration in the tank at any given time is going to be equal to however much salt is in the tank, so our variable x, divided by our volume at that time, so 70 plus 2t, and this is equal to our concentration in the tank. And so we can rewrite our initial derivative expression as dx over dt is equal to 15 minus 3 over 70 plus 2t multiplied by x. We can add our second term to the left side of our equation, and so we will get dx over dt plus 3 over 70 plus 2t multiplied by x is equal to 15. This expression looks just like the expressions we used in the earlier problems, and so our p of x must be equal to 3 over 70 plus 2t. From that, we can obtain our integrating factor of rho of x is equal to e to the integral of 3 over 70 plus 2t dt. Solving this integral and simplifying this expression, we get rho of x is equal to 70 plus 2t to the 3/2 power. Multiplying this factor by each term in our original expression, we get x prime, which is the same thing as dx dt, multiplied by 70 plus 2t to the 3/2 power plus 3 over 70 plus 2t times x times 70 plus 2t to the 3/2 power is equal to 15 times 70 plus 2t to the 3/2 power. Some quick simplification of our center term, 70 plus 2t to the 3/2 over 70 plus 2t, will simplify to 70 plus 2t to the 1/2 power, and so we have x prime times 70 plus 2t to the 3/2 plus 3x times 70 plus 2t to the 1/2 is equal to 15 times 70 plus 2t to the 3/2. The left-hand side of our equation is equal to the derivative of x multiplied by 70 plus 2t to the 3/2 power, and this will be equal to 15 times 70 plus 2t to the 3/2 power. Taking the integral of both sides of this equation, the integral will cancel with the derivative, and so we have x times 70 plus 2t to the 3/2 power is equal to the integral of 15 times 70 plus 2t to the 3/2 power dt. Solving for the integral on the right-hand side of our equation, we then get x times 70 plus 2t to the 3/2 power is equal to 3 times 70 plus 2t to the 5/2 power plus some unknown constant c. Dividing both sides of this expression by the quantity 70 plus 2t to the 3/2 power, we can simplify to x is equal to 70 plus 2t to the 5/2 divided by 70 plus 2t to the 3/2 will give us just 70 plus 2t, and then we can distribute the 3, and so we will get 210 plus 6t plus some constant c multiplied by 70 plus 2t to the negative 3/2 power. We now need to solve for our unknown constant c. Given that we know that there was initially no brine in the tank as it was pure water, we can say at time of 0, x is equal to 0, will be equal to 210 plus 6 times 0 plus the unknown constant c multiplied by 70 plus 2 times 0 to the negative 3/2 power. Solving this equation for c, we find that c is going to be equal to negative 210 multiplied by 70 to the 3/2 power. And so we can write our complete expression for the amount of salt in the tank at any given time of t as x as a function of t is equal to 210 plus 6t plus negative 210 times 70 to the 3/2 power times 70 plus 2t to the negative 3/2. Rewriting that expression in a little bit of a cleaner way, x of t is equal to 210 plus 6t minus 210 times 70 to the 3/2 power over 70 plus 2t to the 3/2 power. And so we have found our expression representing the amount of salt in the tank at time t. That concludes today's video on how to solve linear first-order differential equations.